Hello everybody, welcome. This is paper 1 from Time Zone 1, May 2023. Let's take a look and see what we can do. Alright, first things first, this is the rubric, often kind of neglected. One careless or unfortunate way to lose marks is given right here. It says, unless otherwise stated in the question, all numerical answers should be given exactly or correct to 3 significant figures. So to give something an exact answer would be, for example, to write it as root 2. If you wanted to as well, if it asks you to give it an exact answer, then it needs to be given an exact answer. But if you do use decimals, for example, they should always be given in 1, 2, 3 significant figures. So sometimes they'll ask you, sometimes they'll state round to the nearest dollar, sometimes if it's a financial mathematics question, it's $2 and cents, 2 decimal places. Sometimes it can be given exactly, but if you do use decimals and so on, 3 significant figures. Alright, just be mindful of that. Often an unfortunate way to potentially lose marks. Okay, so let's work through this and see what we can do. Here's question number 1. It says, the decathlon is a competition where athletes compete in 10 events. 2 of those events are long jump and high jump. In both events, a greater distance means a better ranking. The table shows results for these 2 events at the World Championship. And then we see the long jump scores, the high jump scores, and then their various scores for each country. Further on down, it says, the Spearman's rank correlation coefficient is used to determine if there is a linear correlation between an athlete's ranking and their ranking in high jump. So their ranking in long jump versus their ranking in high jump. Complete the table below to show the athlete's rankings in high jump. And then part B says find the value of Spearman's rank correlation coefficient. So they've already given us the rank for long jump, where the highest score takes the highest rank. And we can do the same thing for high jump over here. So we see Germany 2.11 would take the highest rank. And then going down from highest to lowest, we can complete the rest. This is the second, this would be the third for the Netherlands. And this is a common question for Spearman rank correlation. They'll give you a situation where there's 2 values that are the same. And when it comes to ranking these, we can ask the question, okay, well, do they both take the 4th? Do they both take the 5th? And it's actually neither. They would take the average of the 2. So 4 plus 5 divided by 2 gives us 4.5. They would both share this value. So this would be 4.5, 4.5. And then another little trick after, if we already have the 1st, 2nd, 3rd, 4th, and 5th ranking, respectively, we continue to count from that value. So going on down, Grenada would take the 6th ranking. It's the 6th highest score. And then this would be the 7th. This would be the 8th. And then we have the 9th and the 10th highest score. And then we have the corresponding long jump ranks and high jump ranks for each of the countries. And this is important because when we enter these values to find Spearman's rank correlation coefficient, or RS, we need to make sure, and we can treat these as, in some sense, a coordinate pair and enter these into our calculator. So let's go ahead and do that. Let's complete part B, where it asks us to find the value of Spearman's rank correlation coefficient. Alright, so let's go to calculator right here, and let's look at spreadsheets. Let's label. We can do long jump and high jump, or X and Y. Let's just use X and Y for this. I think that's fine. And let's put in the rankings just as they're presented to us. So long jump rank, these were already ranked for us. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's put the corresponding values. So if you remember, Germany had 1, 1. This was France, 2, 2. And then Estonia had the 3rd highest long jump rank, but the 10th highest high jump rank. So remember, these are kind of coordinate points. They need to be in pairs. All right, and let's just fill in the rest right here. 3, 4.5, 8, 9, 6, 7. All right. And to find Spearman's correlation coefficient, it's a similar process to finding Pearson's. We put the values in the spreadsheets, label our columns, and then we run 2 variable statistics. So statistics, stat calculations, 2 variable statistics, calculator asks where did we put our x values. This would be long jump. This is our high jump. And then we press enter, and that's all actually we need to do. Okay, so let's go down to find r. This is the same r that we would use for Pearson's, but since we provided our values and we ranked them, what we have now is Spearman's correlation coefficient. So that's our correlation, our Spearman's correlation coefficient, 0.541. All right. So let's go ahead and go back to the document. Here we are. Question 1 continued. Let's actually put that down. RS is equal to, this is our value, 0.541 to 3 sig figs. I'm putting it here, but remember at the very beginning it says all answers must be within this box. So please be mindful of that. This would open up a little nicer, one page on each, let's say, side, left and right. So actually, let's do it. This is what we would probably put. RS is equal to 0.541, and of course putting A in here above. Actually, A is the ranking itself, so that's already done. All right, let's go on to C and see what we can do. The following guide is used by the coach to determine the strength of the correlation between the ranks for long jump and high jump. And now we want to categorize what is this 0.541 according to this scheme right here. State the strength of the correlation between the rankings is indicated by the table and interpret this in the context of the question. So we see 0.541 falls within this moderate classification. So C, we would say this is a moderate, it's a moderate correlation, but quite important in this question, it's a 2-mark question. State the strength of the correlation between the rankings indicated and interpret this in the context of the question. So we would say moderate correlation between, what could we say, high jump rankings, long jump rankings, and high jump rankings. Long jump rankings and high jump rankings. High jump rankings. So for a 2-mark question, make sure to read the question carefully, and if it asks you for something to interpret this in the context, it's not enough to simply write moderate. That would be A1. That would give you one answer, but not two. Actually, maybe it's not a bad idea to look at the mark scheme in this case to show you what they're kind of looking for. So here we are. Here we go. So RS, that's what we have, 0.541, and we have, whoops, a moderate correlation. I'm sorry about that. A moderate correlation, and then we have, as long jump ranking increases, high jump ranking will increase as well. Moderate correlation between long jump ranking, high jump ranking, or I guess this is even a little more kind of contextualized, I suppose. As long jump ranking increases, high jump ranking will increase as well. Alright. Part 2, looks like we have a trigonometry question here. Point H on a hot air balloon is sighted at the same time by 2 observers. One observer is at the top of a vertical building that is 156 meters tall. The other observer is at the base of the building. The angle of elevation from point A at the top of the building to H is 40 degrees. So from point A, we're talking about this line right here, sorry, this angle. And the angle of elevation from point B at the base of the building is 57, and that would be right here. Point X is the ground directly below H, and this information is shown in the diagram. Okay. First question, they ask us to find the size of AHB. And so when we're trying to find AHB, a helpful way to kind of remember this is whatever the top hat, wherever this top hat is, that's the angle that we're looking for. We also see this presented as AHB, where again we're looking for this center value. Tracing out the points themselves will also be a helpful way to see what angle they're referring to. So if we have A going to H, going to be, we see that we're looking for this theta value right here, AHB. All right. So a few different ways that we can solve this, and there's a lot of kind of creative ways. I'll show you the one that is kind of, I guess, appears most readily to myself. And if you found a different way, that's great as well. So here we have this triangle. AHB would form itself a triangle, and we know interior angles of a triangle sum to 180. So let's see if we can find the two interior angles, and then we can find this missing one right here. So if we're looking at this building right here, we know the edge of this building with the ground will form a right angle. And that means we're going to have what are called complementary angles. And so if this is a 90-degree angle, and we see 57%, or sorry, not 57, but 57 degrees is right here, then we know that the remainder would have to be 23 degrees. And similarly, if we're talking about this line that's parallel with the horizon, then we know that we're similarly going to have a 90-degree angle here. So if we were to complete this, we would have 90 degrees and then altogether 130 degrees. So if we know the interior angles of this triangle, we can go ahead and find the missing one, because we know that angles of a triangle add to 180. So we have essentially 130 plus 23 degrees plus our theta value should equal 180. You can write this as your process, or you can write 180 degrees minus, and then adding these two together, which is going to give us 153 degrees. Minus 153 degrees is going to give us the remainder. And in this case, theta itself would equal 27 degrees. Okay, next question is calculate the distance from point B to point H. So if I can just maybe say this once again, 2-mark question. They're probably expecting something like this, and then the answer itself. So just the answer won't be enough for complete method marks as well. Part B, calculate the distance from point B to point H. Let's clear some of this up. Point B to point H. Okay. Point B to point H. So in that case, they're asking us about this value right here. What is the length of B to H? All right. So I think it's helpful to kind of categorize the question and see what kind of domain we're in, I suppose. And since we have the length of a side length of some triangle, and we know we have all of the angles of this triangle that we're working with this side length here, this side length, and this side length, we're in the realm of non-right angle trigonometry. Non-right angle trigonometry, we can reduce it to 3 kind of formulas that we can essentially use. Sine law, cosine law, and then the area formula. Sine law is always going to be the easiest one to use, so let's see if we can use sine law, and then if we can't, then we might need to go to cosine or area. Alright, calculate the distance from point B to H. Sine law, remember in our formula booklet, is just going to be A over sine A equals B over sine B, where this is the side length and this is our angle, of course. And if we have a side length and its opposite angle, or an angle and its opposite side length, and an angle and its opposite side length, 2 pairs of these, then we can solve for the unknown. So let's see if we have that. We know that this, for example, was 130 degrees. We found out earlier that this was 23 degrees, so we have all the angles. And if we can just find one side length, we should be able to use the sine law. It doesn't look like we have the sine length, but here we know that this building is 156, and we would therefore know that, unless this is a rather peculiar building, we can imagine that this as well would be equal to 156. To be honest, it is actually a peculiar building because it's 156 meters for a 2-story building, which is already a little ridiculous, but all the same. Okay, so let's go ahead and see how we can apply the sine law. So we have an angle and its opposite side length, and this right here is the side length we want to find. So let's use the angle and its opposite side length and work that out. So we have 156 side length over angle, which is sine 27, is equal to, and then we don't know what AH is. Let's just call it x. And we have x over sine B, and we said it was 130 degrees. Let's go ahead and put that into the calculator. Alright, let's go ahead. And to be honest, you could perform some algebraic manipulation, but I'll show you through nsolve if you'd like. So let's use numerical solve, and then let's put this value in. So let's get a fraction here, 156 over, and let's go trig sine 27. So now that we're entering trig, actually, I'm just thinking of this myself. In the top right corner, we're now in radians. That would be unfortunate. None of the AISL is in radians. You won't need to use radians at all. Make sure that you are in degrees. Let's go ahead and change that to degrees. So you should see DEG, degrees, instead of RAD, radians. Alright, so we're halfway to completing this. 156 over sine 27. Let's put some variable. Let's put x. That should be fine. Set it up as a fraction first. And we'll put x over, and we'll put sine 130. Sine 130. And let's ask the calculator to solve for x. 263. Alright. So let's go back to the paper, and let's write calculate distance from B to point H. For process, I'm just actually going to circle this in. This is essentially what would count as process right here. And we could write point B to point H. Let's write it a little better, I guess. BH, our side length BH, is equal to 263. So side length BH in this case. Okay, and that's it. If we wanted to, I suppose we could write it as meters. Alright. The hot air balloon remains at a constant height as it moves further away from the building. Describe in words the change in the angle of depression from point H to point B as a horizontal distance between the balloon and the building increases. So I'm just going to sketch out what happens. No, I'll use this over here. So the horizontal distance remains the same, but this balloon travels off into the distance. And angle of depression itself is our line, sorry, the value that we need to sweep through from the horizon. And I'll actually show you what that means. So if this is our horizon line right here, the angle of depression is the angle that we must sweep through looking down from the horizon. And as we go off into the distance, if this is our first angle of depression, this theta right here, we can ask ourselves the question, what happens as we go further and further away? As we go further and further away, theta value will decrease. So if this is theta 1 and this is theta 2, we know that theta 2 is less than theta 1. And we can imagine stretching this far into the distance, and the angle that we need to sweep down becomes less and less and less. So for this 1-mark question, describe in words the change in the angle depression from point H to point B. So from here to point here, even worse actually. So here we go. This is actually the angle that we're looking for. So we can see this is actually going to give us a better kind of view. So it's this theta 2, and this would be theta 1. Theta 1. So the angle of depression becomes less and less and less and less. Describe in words the change in the angle of depression from point H to point B as a horizontal distance between the balloon and the building increase. We can write as horizontal distance increases, increases, angle of depression decreases as well. If you're super short on time for a 1-mark question, they're often just looking for keywords. We can actually find that here and see what that looks like. Alright, so that's actually the earlier one, sine rule, right here. Interesting attempt to use sine rule is enough, actually, for 1 method mark. So the angle of depression from the hot air balloon, so all they're actually looking for here is gets smaller. That would be enough. Okay. Once again, remember to write all of your values within this box. Alright, on 1st of January 2022, Mina deposited $1,000 into a bank account with an annual interest rate of 4% compounded monthly. At the end of January and the end of every month after that, she deposits $100 into the same account. Calculate the amount of money in her account at the start of 2024. Give your answer to 2 decimal places. And after that, it's find how many complete months counted from 1st of January 2022 it will take for Mina to have more than $5,000 in her account. So let's start through A. This is a financial mathematics question. So in this case, we want to get out the calculator and go into finance and finance solver, bringing finance solver up. Let's actually put down all of the values that we have. We have n, I, and then this is as a percent, remember. We have present value, PMT, the number of payments that we make, or not the number of payments, rather the payment amount that we make. Then we have PPY, and we have CPY, and then at the very, very end we have payment at. So when are you making your payments? And by and large, you might get a rare question where this isn't the case, but by and large, payments are made at the end of the month. The bank pays you at the end of the month, at the end of the year, and so on. Alright. So, let's see. We can actually use our compound interest formula for this one as well. And maybe that's actually not a bad idea. I'll show you how to do that as well. But let's use a financial solver first. It's a little versatile if you're comfortable with it. It's probably more versatile, but sometimes it's safer to use the compound interest formula. So let's see. January 1st, 2022, she deposited $1,000. So 4% interest, compounded monthly, and she makes, at the end of every month, $100 payment into the same account. Actually, so since she's making regular payments, we won't be able to use compound interest formula. In this case, we're actually going to need to use the financial solver. So regular payments into an account, we can no longer use compound interest. Compound interest is you put money into an account and you leave it there, and it's going to grow or potentially decrease, I suppose. But we're not making any kind of additional contributions. There's no money flowing out, or we're not making deposits ourselves into this account through time. So we need to use a financial solver here. Alright, so working through this, let's work through interest rate first. That's often the most straightforward. Interest rate as a percent is 4. The present value, or the initial starting value, is equal to 1,000. And a helpful way to remember, of course, is money flowing out, money flowing in. So let's put a negative 1,000. It's money flowing out of the individual. What else do we have? We have Mina making deposits, $100 into the account every month. So in terms of payments, she's making a deposit of $100 every month. The final value, we want to find the final value, the money in her account in 2024. So the final value is what we're trying to find. Payments per year, it says she's making them every month, so she's making 12 payments per year. The interest itself is compounded monthly, so compounding periods per year. Compounding periods per year is 12. And then payments, of course, is at the end. Bank account and interest at the end. All right, and the number is how many payments per year are we making, and then times the number of years. So if it starts in 2022 and goes all the way to 2024, the start of, we started in January as well, we have 12 months times 2 years, or 24 years. So let's go ahead and enter that actually into the calculator. Let's go ahead. So 24. Actually, I'll show you how to get there as well if you're unsure. So menu, finance, financial solver, of course. All right, 24, total number of payments, interest rate is 4%. Present value, $1,000 flowing out. Payment, again, $100 flowing out. Final value is what we want to know, so we'll leave it blank. Payments per year, 12 payments per year, 12 compounding periods per year. Bank pays us 12 times a month, I suppose. And payment is at the end. Let's go ahead, highlight this value, press enter, and there it is. Okay, 3,577.43. So often financial mathematics questions, they may specifically ask you to round to the nearest dollar, but they'll generally state it, and here it is to 2 decimal places right here. So 3,577.43. Here's part B. Find how many complete months counted from 1st January 2022 it will take for Mina to have more than $5,000 in her account. I'm going to quickly write this out once again. PV and so on. PPY, CPY, and then payment at. Okay, so let's see what we can do. How many complete months? So in this case we want to know N. The interest rate remains at 4%. For how many complete months it would take for Mina to have more than $5,000? The present value, it appears that the situation is the exact same, except there should be one variable that is changing. And in this case, it's the final amount. The final amount of $5,000 is what she wants in the account. So let's look. How many complete months? So interest rate is 4%. Present value, she still deposited $1,000. She's still making $100. The final value, we want $5,000. This is positive because it's money coming towards her, money readily available to her. Not something that she has now, in this case, like locked up in an account, that she's flowing out of her. This is money coming towards her. Payments per year, she's still making 12 and the bank is still paying 12, and it still all happens at the end. All right, let's go ahead and enter this into the calculator. Here we are. So N, we're going to want to change 4, -1,000, final value. Okay, this looks good. Press enter, and it looks like we have, just going back to the document itself, 36.5 months. And of course, again, how many complete months? How many complete months will it take? So how many complete months will it take? 36.5 months, she has exactly 5,000. That means at 36, she doesn't quite have that much. It's not until the 37th month, actually, that she has this $5,000. 36.5, the bank doesn't pay you halfway, they only pay you at the end of every month. 36 months, she doesn't quite have enough. She'll probably have 4,900 and something, or maybe a little less, actually. But at 37 months, now she has more than the 5,000. 36.5, not quite yet. So here it is, 37 months. All right, let's go to question 4. Carries believes that on a memory retention test, the mean score of bilingual people, so mu of b, mean score of bilingual people, will be higher than the mean score of monolingual people. Carries gave a memory retention test to a random sample of students in our class. The results are shown in the two tables. These are the scores of bilingual people, and it might be helpful to actually write this out, mu of b. And these are the scores of the monolingual people, mu of m. So this is the mean score of each. Carries performs a one-tailed t-test at a 5% level of significance. It is assumed that the scores are normally distributed. This is an assumption we always make. This is essentially saying pooled equals yes. This is generally the case actually for all AI. At the end you put pooled is equal to yes. And the samples have equal variances. State the null and alternative hypotheses. So we've got a t-test, and t-test compares the means. So let's write HO and H1. So the null and the alternative hypotheses. The null hypothesis is the status quo. It's the idea that there's nothing to see here. And that's the idea that the mean score of bilingual is equal to the mean score of monolingual. And the alternative is that, now we might need to be careful because there's a few situations. We can either have one being greater than the other, less than the other, or the same. So it depends on her intentions here. Let's read it through again. The mean score of monolingual people. So she wants to see if the mean score of bilingual people will be higher than the mean score of monolingual people. So she wants to see if mu b will be higher than mu m. And that would be the alternative in this case. Mu b is greater than mu m. This is important, especially on a t-test, so please be careful of this. If this isn't the case, and if this one is incorrect, then this will be incorrect, and this potentially you can get some error carried forward if your results are still consistent with themselves, but a lot actually hinges on getting this first part correct. So there it is. All right, calculate the p-value for this test. Let's go ahead and go back to the calculator. All right, let's exit this. Here we go. And in this case, we're going to go back to spreadsheets, and I guess we can write bilingual and monolingual. We can write X and Y for these all the time. Just in case you're wondering, it shouldn't matter that they have a different set of values for each. That is to say that bilingual people have more than monolingual, more participants. Let's see, they have 10 participants. Yeah, that's correct. And here we have the monolingual individuals. 97, 92, 88, 98, 88, 94, 100, and 100. Okay, so make sure these are all incorrect, or that these are all correctly in. Good, good, and so on. Okay, good. Let's go ahead and statistics. We want to do a statistical test. In this case, we have a two-sample t-test. List 1, this would be our bilingual. List 2 is our monolingual. We don't have any frequencies. They're all just as they are. And alternative hypothesis, we're saying that mu1 is greater than mu2. That is to say, bilingual are greater than monolingual. And this is actually kind of dangerous. Pooled is always yes. Pooled is always yes. So we've got equal variances, normally distributed. By and large, pooled is yes. To be honest, I don't think I've seen a question where pooled isn't yes. I believe it's always going to be yes. All right, let's run our t-test. Let's go down and look for our p-value. There it is, 0.001. 119. Okay. Here's part B. Let's go back to the document. P-value is equal to 0.119. State the conclusion of the test in the context of the question. So again, in the context of the question, justify your answer. So first thing we want to do is we want to compare this p-value to our significance level. So what can we say? We can say that 0.119 is greater than 0.05, or similarly 11.9% is greater than 5%. So what does this mean in terms of the null and alternative hypothesis? What we're saying is that the chance of these results, or us seeing these results just based on chance, on probability alone, is 11.9%. And that's small, but it's not small enough for us to say that, hey, there's something going on. It's not enough for us to reject the idea of the null hypothesis, the idea that there isn't just both of these values being the same. 11.9%, we're going to see these results just based on probability alone. It's not that great, but it's not low enough for us to say, there's conclusively, some kind of difference between these two groups. So in this case, we fail to reject null hypothesis, or the null hypothesis. Fail to reject the null hypothesis. And what can we say in context? We can say no significant difference between mean scores of bilingual and monolingual individuals. Let's go ahead and see what the mark scheme has to say about that. Okay. There we go. Fail to reject the null hypothesis. Insufficient evidence to suggest that bilingual people have better memory retention than monolingual. Alright. Alright, let's keep going. Line L1 is tangent to the graph of f of x at point P, 3, -1. Line L2 is given by the equation y equals -1/2 x minus 5/2 and is perpendicular to L1. Write down the gradient of L1, find the equation of L1 in the form of y equals mx plus c, and show that L2 is not the line that is normal to f of x at point P. Okay, so let's see. We know that L2 is equal to, actually let me put a colon here. L2 is y is equal to -1/2 x minus 5/2, and it's perpendicular to L1. So we know that L1 is perpendicular to L2. Here they're asking us to write down the gradient of L1. So if we know the gradient of L2 is -1/2, that's our m in our y equals mx plus c, it's equal to -1/2, and we know that it's perpendicular, L1 is perpendicular to L2, we can take m of L1, let's even write this, m of L2, which is equal to -1/2, and m of L1 is going to be perpendicular, so we want to write the perpendicular. In this case, what we'll do is we'll switch the top and the bottom and multiply by a negative. Take the negative reciprocal. So it'll be 2 over 1, and then it used to be a negative. Let's multiply by a negative. It'll just have a value of 2. There it is. So the gradient of L1 is 2. For part B, find the equation of L1 in the form of y equals mx plus c. Okay. So we already know the gradient of L1 right here is equal to 2. So we have y is equal to 2x plus c, where c is our y-intercept. We don't yet know c, but we can find it if we have 3 unknowns right here. We have x and y and c, but we do have a point on the line, L1, tangent to some graph, and it's at the point 3, -1. So if we have some function like this, and let's say it's tangent to this line, and this is L1 right here, this thing right here is f of x. If we're tangent to the line, it means we have a point on the line. So we know we have 3, -1, which is on L1. So if we have a point on the line, and we know an x and y value, that is to say we know that this is 3, we know that this is -1, our x and y value right here. So let's go ahead and substitute. Y is equal to -1 when x is equal to 3, and we want to find c. And you can end solve here if you want. This can be -1, 6 plus c, or c itself, bringing this over, is equal to -7. So in the end, what we have, y is equal to 2x minus 7. And that would be our answer. Show that L2 is not the line that is normal to f of x at point P. So here's L1 right here. And if these lines are perpendicular, that means they would intersect at a right angle. And we're also saying that this line, L2, is at this point. Or actually we're saying it's not the line that is normal to f of x. So we know that these things are perpendicular, so they pass this kind of criterion, or this kind of check that we would ask ourselves. Okay, well, is it perpendicular? Well, if L1 is tangent, and this is perpendicular to the tangent, then it is normal. It's normal to L1, but is it normal to f of x, this function, at the point P? And there are a few ways to possibly check this. The first one we might want to ask is L2 actually at the point P? Do we have an equation for L2? We do. This is L2 right here. So let's write this out. Give ourselves a little more space. Here we go, for C. So we know that L2, I'm just rewriting this as 1/2 x minus 5 over 2. And we're asking the question, is this a point on the line when y is equal to -1 and x is equal to 3? We're asking, is it a point on this line right here? So let's substitute this value in. Let's substitute this point P, 3, -1. Y is equal to -1, x is equal to 3, and this is equal to -5 over 2. Let's do a little bit of algebra. -3 over 2 minus 5 over 2. This should be -1, and this will be -8 over 2, which is essentially saying that -1 is equal to -4, but that's not true. So it is not at the point P. So it can't be normal to the line. Although it's perpendicular to L1, it's not on the point P. It's not at the point P. We substitute the values in for x and y into this equation, and we find we get a contradiction. Every point that we substitute into some equation should balance if it is on the line, if it satisfies this equation, and it doesn't in this case. Alright, let's see what we can do. Alright, just about halfway through. When the brakes of a car are fully applied, the car will continue to travel some distance before it completely stops. the stopping distance d in meters is directly proportional, this is important, directly proportional to the square of the speed of the car v. So stopping distance d directly proportional to the speed of the car v in kilometers per hour. So stopping distance is directly proportional to the speed of the car squared, the square of the speed of the car. We'll unpack this a little more in a sec. When a car is traveling at 50 kilometers an hour, it will travel 12.3 meters after the brakes are fully applied, before it comes to complete stop. Determine an equation for d in terms of a. So d in terms of means we want d all by itself. D is equal to, and then something over here. So what do we know? We know that these things are directly proportional. That is to say, the stopping distance and the square of the speed of the car. Whenever we have directly proportional relationships, we're going to have this form of something is, and this is called directly proportional, this symbol right here, directly proportional to, in this case, the speed of the car squared. So just a little kind of overview on directly proportional relations, because this is sometimes a little funny. Often we have linear equations, and linear equations themselves can begin, or they can cut the y-axis anywhere. We can have a linear equation that goes up, a linear equation that goes down. But what we're talking about when we're talking about directly proportional, and we have, let's say, two variables, y and x. For directly proportional, it always goes right through the origin, no matter what. And so what we have essentially is an equation of a line, y is equal to mx, but we don't have any y-intercept, because the y-intercept is just 0, essentially, so plus 0. And so directly proportional relationships are essentially linear equations, except they go through the origin. A quick example, this is going to be a whole lesson on it, but a quick example of a directly proportional relationship. Actually, let's even use a table as well. If we have, let's say, the cost of a number of buttons, and if we have buttons and the cost, and we buy, let's say, 5 buttons for $25, 10 buttons for $50, the cost that we need to pay is directly proportional to the number of buttons that we buy. And we're looking for some kind of factor. If we're saying that cost is directly proportional to the number of buttons, we're looking for some kind of factor, what we call a proportionality constant, to multiply b by the number of buttons in order for us to get the cost. And in this case, just looking at it, we say, okay, well, if we buy 5 buttons, it costs 25. 10 buttons, it costs 50. In this case, this proportionality constant, k, is just the cost per button, essentially. And this would be 5. So cost is, let's say, 50. K, we don't know what it is, or we imagine we don't know what it is. And we buy 10 buttons. What must k be to satisfy this equation? So getting back to this, determine an equation for d in terms of v. If that was all, potentially, and I hope not, but potentially a little kind of mystifying, proportionality constants, proportional relationships, or what also called direct variation problems. Anytime you see this, directly proportional to, we have this situation where some variable is equal to, in this case its distance, is equal to whatever the other variable squared, whatever the other variable is. It doesn't necessarily have to be squared, it can be cubed or just by itself, but it's equal to k, some proportionality constant. So if we have the distance is proportional to the square of the velocity, what we're asking is, what is this proportionality constant? What do we need to multiply our velocity squared by in order to get distance? And so let's plug in some values. Distance is equal to 12.3 in this instance. K is what we want to try to find out, and the speed at this time was 50 squared. So 50 meters per second, or kilometers per hour, and then we want to square this. So let's just use a calculator. We can n-solve this. 50 squared, 12.3 divided by 50 squared is going to give us a value for k of 0.004921236. Alright, determine an equation for d in terms of v. So going back, d is equal to 0.00492 v squared. And that would be our equation. Use your equation, or let's actually, sorry, read this. The police can use this equation to estimate if cars are exceeding the speed limit. A car is found to have traveled 33 meters after fully applying the brakes before it comes to a complete stop. Use your equation from part A to estimate the speed at which the car was traveling before the brakes were applied. So let's see. The distance that this car traveled, for working on part B right now, the distance that this car traveled was 33 meters. We know our proportionality constant is 0.00492, but we don't know the velocity that this car was traveling. And our relationship also requires that we have the square of the velocity. So we can n-solve this again. Let's take 33 divided by 0.00492 and take the square root of that. If we n-solve this, or if you want to work it out algebraically, of course, we see that the car was going 81.9 kilometers an hour. Alright, which the car was traveling, and I think that was it. That's actually not that bad. Alright. Is there anything else to say on that one? Estimate the speed? Potentially. So let's say this was like mystifying, right? Always, it's somewhat unfortunate. I mean, if you have the time, don't leave any marks just kind of like on the ground, like left unattempted. So the correct answer to part B depends on part A being correct. But the question is, like, can you potentially make something up, make some equation up, and then substitute some values into this to potentially show that, yes, I can still have an equation, substitute into it. I recognize that this is velocity squared, although I haven't found the proportionality constant to reach some value that is hopefully reasonable. If the car is going like 6,000 kilometers, it's ridiculous, but potentially, at a 2-mark question, you might have some kind of error carried forward. It might itself hinge on this part A being logical, or at least logically consistent, but to leave 2 marks on the ground, potentially you could substitute values in as long as this is squared and come away with some process marks. Alright, after the brakes have been fully applied, identify one other variable besides speed that could affect stopping distance. One other variable besides speed, it's after the brakes have been applied. You can think of anything really. Slippery roads, maybe it's raining. Something like that. Alright, question 7, let's see. A rectangular box with an open top is to be constructed from a piece of cardboard that measures 48 centimeters by 30 centimeters. Squares of equal size will be cut from the corners of the cardboard as indicated by the shading in the diagram. The sides will then be folded along the dotted lines to form a box. And then we've got the dimensions here, 48 by 30. The volume of the box in cubic centimeters can be modeled by the function v of x is equal to 48 minus 2x, 30 minus 2x times x. For some value of x being greater than 0 and less than some value k, where x itself is the length of the sides of the squares removed in centimeters. Write down the maximum possible value of k in this context. So, let's see. For this question, the most challenging thing might be interpreting what it's asking. What they're asking for here is they're saying, okay, well, if x is the length of the sides of the squares, this x right here, to be removed, we know if we're going to remove anything from these boxes, it has to be something. If x is equal to 0, then we're not actually doing anything to this piece of paper, this piece of cardboard. We're not going to create a box. And x has to be greater than 0, but it also has to be less than some value k. And to put that in real-world context, We're asking what is the largest size cutout that we can make from this piece of cardboard while still being able to create a box. And of course, if the dimensions are 48 by 30, what are we talking about? Well, if we suddenly create a box and cut out, let's say 15 by 15, we no longer have a cardboard box. Essentially, if we do that to both sides, we're just going to have a strip of paper. We're going to have a tough time, to say the least, creating a box. So, in this case, what's the maximum value of k? Well, k can be greater than 0, right? It can be a little bigger. Maybe this is 3. And if you wanted to, maybe you can make it 10. But once you make it to 15, and it's 15 on both sides, then we no longer have a box that we're going to be able to fold up, or a piece of cardboard that we're going to be able to fold up. So for this 1-mark question, write down a maximum possible value of k. K must be less than 15, not less than or equal to. If it's equal to 15, we still don't have a box. Less than 15, theoretically. Find the value of x that maximizes the volume of the box. All right, 2-mark question. What's going on here? We have this equation right here. And what does it do? It relates volume to the size of the cutouts. And so we're relating these two variables. We can kind of think of inputs, outputs again, but we're relating these two variables, volume and the size of the cutouts. We change the size of the cutouts and we change the volume. We can put in some values of volume and then ask what are the size of cutouts that we would need to make that volume, that true. And in this case, if we're relating these two variables, volume and size of cutouts, we can graph this and find out a maximum. I think that's going to be the easiest way. So find the value of x that maximizes the volume of the box. Let's go ahead and graph. Going back to the calculator here. All right, here we are. So let's write 48 minus 2x, 30 minus 2x, and then multiplied by x. Okay, this looks like a straight line. Don't be dismayed. Why is that? The IB will often give you things like this. It's not that you entered something wrong in this case, although potentially that can happen. In this case, it's just a massive, massive function that's growing really, really quick. And our y value is actually pretty small. So the volume, it's never going to be that small. Not really. I mean, it potentially can, but the problem here is that our window is too small. So let's go, and let's try zoom fit first. Zoom fit actually doesn't do too bad of a job. So we change the size of the cutouts and we change the volume. We've got a good graph here. So let's go analyze the graph and let's find the maximum. There it is. So when we have a size cutout of 6 right here, we've got a pretty big volume. Okay. Find the value of x that maximizes the volume of the box. I'm actually going to write down this right here. And so we can say when x is equal to 6. How would we show this, to be honest, to make sure we're getting method marks? Something like a graph. 6, and then this 6.89 e to the 3. The IB isn't going to like e to the 3. So let's write it out as 6.89 times 10 to the 3. 6.89 times 10 to the 3. 6.89, 1, 2, 3 hops. 6,890, in this case, centimeters squared. That's our volume. Okay, let's go ahead to part C. A second piece of 48 by 30 centimeter cardboard is damaged, and a strip 2 centimeters wide must be removed from all 4 sides. A box will then be constructed in a similar manner from the remaining cardboard. Calculate the maximum possible volume of the box made from the second piece. Okay, so let's get some space down here. I'm going to erase that actually, and we'll see what we can do. So again, interpreting the question it's a geometry question, so it's always going to be helpful to sketch it out, and I think that will be the case here. So let's go ahead and draw. Hopefully this gets a nice square. No? Okay. Here is our rectangle. Dimensions, like the original one, are 48 by 30. But there's been, it's been damaged. It's been damaged by the rain. And we need to remove a 2 centimeter strip from all 4 sides. So what's going to happen is we need to remove 2 centimeters along here, 2 centimeters along here, 2 centimeters along here, and 2 centimeters along here. And so we're left with a box after we tear these out that's going to be a little smaller. We're cutting out a 2 centimeter strip here, and we're cutting out similarly a 2 centimeter strip here, and so on. So let's just look at this 48 dimension first. If this is 2 centimeters and this is 2 centimeters, then overall this new dimension right here is going to be 48 minus, and then we have two 2 centimeter strips. It's going to be 48 2 by 2, or 48 minus 4, or 44 centimeters. Same here. This dimension used to be 30, but since we're taking off 2 centimeters from each side, we're only going to have a dimension of this inner box, which is going to be 26. And lastly, this one again is going to be 44. So we've got a smaller box. It's now 44 by 26 because we took 2 centimeters off from each side. Now calculate the maximum possible volume of the box. We already have a situation where we relate volume to the size of the cutouts. So let's actually just draw from that. This 48 was related to our original dimensions, and this 30 was related to our original dimensions as well. If we fold this up, we're going to get a box with a base of 44 by 26. And we can, rather than go into a more lengthy explanation, let's just model a relationship between size of cutouts and the volume based on what we have here. So v of x, or we can just write volume, is equal to 44 minus 2x, 26 minus 2x, 26 minus 2x, and then of course this is still going to be x. If we want to find the maximum possible volume in this case, let's go back and graph it. So let's go back into calculator screen and let's see what we can do. 44 minus 2x, 26 minus 2x, and then lastly times x. Again, we get a vertical line. Let's go ahead and zoom fit, adjust the window, analyze graph, and find the maximum once again. Here we go. Going back to the document, the maximum possible volume of the box, maximum possible volume occurs at 5.28, and the max volume is 2.73 times 10 to the 3. So remember, calculator gave us this, right? E. So we're saying e to the 3. What that means is, let's take 10 and raise it to an exponent of 3. So this is what we're looking for right here. 2.73 times 10 to the 3. Or 2.73, 1, 2, 3 hops, 2,730 if we want. Okay, that wasn't too bad. And remember, of course, I hope this is okay. All of your answers need to be in here. Alright, this one is getting a little complex. Getting closer to the end, I guess. Password entropy is a measure of the predictability of a computer password. The higher the entropy, the more difficult it is to guess the password. The relationship between the password entropy p, measured in bits, and the number of guesses g required to decode the password is given by this relationship right here. 0.301p equals log base 10 of g. And now they want us to calculate the value of p for a password that takes 5,000 guesses to decode. So this might look a little complicated, but we are essentially in the domain of a kind of input-output situation. So we've got some relationship between p, the password entropy, and g, the number of guesses that it takes to solve a password. So if a password has a high entropy, it takes a lot of guesses. So you might think of this one being like essentially one of the ones that like Google might give you in terms of their suggested passwords. Special characters, capital letters, so on. High entropy, a lot of guesses if we just want to like brute force and try to crack this thing. Low entropy would be like, I don't know, your birthday or something, or like dog or cat. Something that's not going to be difficult to crack just through like brute force methods. Okay, so that's what's going on here. P, difficulty of the password. G, number of guesses it's going to take to try to solve. If there's a value of p, what is the entropy? What is the difficulty level of this password if it takes 5,000 guesses? It's given by this equation, so let's input and try to see what we can do, or try to solve it in this case. So 0.301, let me erase that. 0.301p is equal to log base 10 of g. 0.301, we don't know p, so let's just leave it. And we have log base 10 of g, and this one took us 5,000 guesses. Let's go ahead and actually nsolve this. You can do this again algebraically, but I think nsolve is probably going to be the most common method to solve this, so let's do it that way. Alright, menu, let's go into algebra, numerical solve, and let's go 0.301, and let's just put in a value of p, I suppose, in this case, and it's equal to, and now let's find log. Here's log right here. We're going to need to press Control, log, and it's going to ask us the base. So let's model what the question has given us, log base 10, and then we want to find 5,000 guesses. That's the value of g. Let's ask the calculator to solve for p. There it is. Not too bad of a question. P is equal to 12.2889 or 12.3. Okay. This is a challenging question. Write down g as a function of p. Write down g as a function of p. So back at the document. Okay. 0.301p is equal to log base 10 of g. All right. And we want to write down g as a function of p. So we want to get g all by itself, but it's wound up in this log. So what can we do? What can we do? What can we do? Here's a little explanation on logs. Skip ahead if say I'm going to take the hit. 1 mark, that's fine. Let's see. If we have something like log base 2 of 8, what we're asking is 2 raised to what power gives us 8? And it says, okay, well, 2 raised to the 3rd power gives us 8. If we have, for example, log base, I don't know, 3 of 9, we're saying 3 raised to what power gives us 9? Well, it's 2. And if, let's model maybe a little more on this situation, if we have a situation where it's log base 5 of what equals 2? Essentially, we're saying 5 raised to the 2nd power gives us what? 5 raised to the 2nd power gives us what? Well, the answer is log base 5 of 25. So 5 raised to the 2nd power gives us 25. And so if we try to write this out in a similar way for this question right here, we have 0.301p is equal to log base 10 of g. I'm just going to rewrite this equation, log base 10 of g, so just rearranging it, 0.301p. What we're asking is 10 raised to what power gives us g? 10 raised to the power of 0.301p gives us g. And now we've got a situation where g is in terms of p. Well, there it is. I'll let you do what you want with that. To be honest, logs can be quite challenging. They really can. Alright. Find the number of guesses required to decode a password that has an entropy of 28 bits. Write your answer in the form of a times 10 to the k. Alright, 3-mark question. The first part is probably input-output, or it is input-output, recognizing what are your inputs, what are your outputs, given a function which relates p and g. And then the second part is saying, hey, can you convert this to scientific notation? So let's go ahead. Here's our function once again. 0.301p equals log base 10 of g. Essentially, what I think they would like you to do is use this, but you can end solve this all the same, and it should be okay. So here we've got an entropy, which they told us was p, and it equals to 28. So let's go ahead and put that in. 0.30128 is equal to log base 10 of g. Okay, and let's just end solve that. So, going back to the calculator, let's see what we can do. Menu, algebra, numerical solve, 0.301 times 28. Let's write that. Times 28 is equal to, in this case, let's write log base 10 of g. Oops. And then we'll ask the calculator to solve for g. There it is. Okay. That's a massive, massive number. 2.679 in this e to the 8. This is the second time we've seen this on an exam. Let's go back to the document and see what we can do. So, here we are. So we found that g is equal to, and please don't put this on the test exactly, 2.679, so 68. And then the calculator set this. It said e to the 8. I don't think you'll get any marks for this, to be honest. You might get one mark, I suppose, out of the 3, which would be unfortunate. Because the input-output is already done correctly. Whenever you have this e again, this e, we're saying we have 10 raised to the power of what? In this case, 10 to the 8. So let's write it out again. G is equal to 2.68 times 10. 10 raised to the power of 8. And that's actually all we need to do. So this is a pretty big 2-mark question for just converting calculator notation into scientific notation. All right. And there we have it. So that's it, 2.68 times 10 to the 8. This is a challenging question. I'll be honest, it took me a couple times to read this initially when I was looking through this. There's a point on the graph of the function g of p with coordinates 0, 1. Explain what these coordinate values mean in the context of computer passwords. 1-mark question. We should be able to do this in about a minute or so. I wouldn't spend... Potentially this could be like a kind of black hole or something like that. Don't get sucked into this if it takes too long, but let's work it out. So we've got these coordinate points g of p, and we said this p is our input, and then this is g, the number of guesses. And so let's write a little space over here for d and just try to formalize this. So the password entropy is equal to 0, and the number of guesses it took us is 1. So what does that mean? Password entropy is 0. Password entropy is the difficulty level of a password. Something super massively complex has high entropy. Something easy is going to have a low entropy. This has the lowest of the lowest kind of entropy. It's 0. super easy. And how many guesses does it take? It only takes one guess, or one input for us. What does that mean? If we get it on our first guess and the password entropy is known, it means that, or sorry, the password entropy is 0, it means that the password itself is known. So that would be an answer. The password is known. Password entropy is 0. We get it on our first guess. This is it. If we get it on our first guess, it's because we know it. And it has the lowest of the difficulty possible. All right, let's go ahead and continue on. All right, looks intimidating, but I don't think it's all that bad. Question 9. The cross-section of a scale model of a hill is modeled by the following graph. Here we've got this graph here. It looks like a cubic function, and it is. The heights of the model are measured at horizontal intervals and are given in the table. So the heights of the model given at horizontal intervals. So when we're at 0, we're 0 distance from the origin. We have a 0 height. And when we travel a distance of 10, we are 3 tall. So we've got this point right here. Travel a distance of 10, we're at 3. Similarly, 20 and 8. This is 20, this is 8, and 30 and 9. Last one will do. This is 30, and this is 9, and so on. So they give us the distance from the origin and then the height at that value. Use the trapezoidal rule with h is equal to 10 to find an approximation for the cross-sectional area of the model. I'm going to get the formula book out. Applications, interpretations, AI formula book. Here we are. Okay, so going down to calculus. Here we are. We've got our trapezoid rule. There it is. Let's go ahead and write it out. Trapezoidal rule 1/2 h. H is something we often need to find. That's why it's at the bottom. They're telling us also in this is b minus a over n. In this case, we don't actually need to solve for h. They've given it to us. And then we have y naught minus yn plus 2, and then we have y1 plus y2 plus dot dot dot, all the way to the second last one, yn minus 1. Okay, so trapezoid rule can look a little intimidating, not gonna lie, but once we get familiar with it, it's actually not too bad. So let's see. So we want to find the area under a curve, and we want to do it by using a set of trapezoids. If you forget the trapezoid rule, we know that we have a set of trapezoids. One trapezoid here, one trapezoid here, and you can calculate them manually if you want. Remembering that, for example, if we have a trapezoid, and we're just going to flip this one on its side so it looks like the ones we have here. And this is also given in your formula booklet. If we have A, B, and H, the area is equal to A plus B, A plus B over 2, and then multiplied by H, or in this case, what would be the height if this thing is on its side. So normally our trapezoids are given on their side like this. We're just rotating it. This would be B, A, and then this is, of course, the height. So you can calculate each of these trapezoids itself. There's only 4 of them. But the formula for a 2-mark question is going to be a little more efficient. So let's see. Here's the area in this case. Area is equal to, actually going to give myself a little more space. Area is equal to 1/2. H, they give us 10. These are the segments, essentially the, we say the bases of our trapezoids in some kind of sense. Usually we need to find it, and yeah, let's keep it like that. I was just going to say B we had in our trapezoid rule, we had h is equal to, no, I don't want to actually deal with that now. Don't want to confuse things. That's fine. Okay, so h, they gave it to us, it's equal to 10, and we have y naught and yn. This y naught means the very first vertical distance when we have a value of 0, or let's say the first value in our trapezoid. What is the first height right here? And it is equal to 0 minus, sorry, this should be plus, I don't know why. It's minus right here. And this would be the height of the final side length right here. And again, it's 0. So at 40, it's 0 once again. 40 is our endpoint, the nth point, plus 0, plus 2 times, and then these are all the intermediate heights. It's 2 times because it shares a value here and here. This one as well is going to be multiplied by 2 because it is a side length that's shared, a side length of a trapezoid that's shared twice. So plus 2 times y1 is 10, the height at y1 right here, plus the height at y2, or the second interval, which is 20, plus the height at our third interval, which is, whoops, I'm sorry, this is a mistake. It's not the x values, rather. Our height is 3, our height is 8, and our height is 9. So when we're at our first interval right here, our height is 3, 8, and 9. This is the height of our trapezoids in each of these cases. Let's close our brackets. So the area, an estimation of the area, is going to be plus 9 times 2 times 5. An estimation is going to be 200. All right. It is given that the equation of the curve is y equals 0.04 x squared minus 0.001 x cubed for this range of values, or for this domain rather. Write down an integral to find the exact cross-sectional area. So for our cross-sectional area, we want to find the sum of all the little values, of all the little rectangles from 0 to 40 of this function. And then we want to put dx, those little rectangles. This is always going to be our form. If we want to find the area of under a curve, we would use an integral, and we would have the lower bound, the lower x value, and the higher bound, the higher x value, and so on. Oops, I don't need that. Okay, let's go ahead and put that in a calculator. Okay, let's get a clear screen actually. Menu, calculus, we want to find a numerical integral. Lower bound is 0, upper bound is 40, and our function itself is 0.04x. Oops, 0.04x squared minus 0.001x cubed, and then as a function of dx. All right. Let's go back to the document and write this out. So it's 213.333, or let's just leave it at 213. Okay, not bad. Calculate, oh, I'm sorry. Write down an integral to express the cross-sectional area. That's this part right here. And then calculate the value to 2 decimal places. So this is me making a mistake here. 213.33, 2 decimal places. Okay. Last part, C. Find the percentage error in area found using the trapezoid rule. So percentage error, This is given in your formula booklet. It looks something like this. Percentage error is, and then we have our estimate exact over exact, and then we want to times this by 100%. So let's kind of unpack this and see. The percentage error actually isn't all that bad of a formula. Essentially, you want to find the magnitude of the difference between your observed, or your estimate, and the exact value. So we know that this is the exact value, and this is the estimate. So what is the percentage difference between these two? So let's go ahead and write our estimate minus exact over exact. And what these things do, they're called absolute value signs, I guess. What they do is they don't allow any kind of negatives. So if you get a negative value, it's a positive. We just want to know the percentage difference. We don't want it as a negative. We just want to know the absolute value. We want to know the size of the percentage difference, not if it's negative or positive. So 200 minus 213.33 divided by 213.33. This gives us, and then multiplying, of course, by 100%, this would give us 6.248 or 6.25%. So since it's a percentage error, we want to find this, multiply it by 100, and then it will give us a final percent. And that's the percentage error. Not a bad question. Percentage error, yeah, it's usually kind of near the end when you're dealing with real-world situations, and they want you to show the difference between an estimate and an exact. So estimate minus exact divided by exact. What is the size of the difference as a fraction or a percentage of the exact value? And then write that as a percentage multiplied by 100. All right, number 10. I think 2 or 3 more questions to go. Okay. In a baseball game, Sakura is the batter standing beside home plate. The ball is thrown towards home plate along a path that can be modeled by the following function. And here it is, y is equal to negative 0.045x plus 2. In this model, x is a horizontal distance of the ball from the point the ball is thrown. Okay. Horizontal distance from the point the ball is thrown. So from the batter's mound, or from the pitcher's mound, point the ball is thrown. And y is the vertical height of the ball above the ground, both measured in meters. The outcome of the throw is called a strike if the height of the ball is between 0.53 and 1.24 meters at some point while it travels over home plate. The length of home plate is equal to 0.43. Okay, a lot going on here. Always recommend to underline keywords. Alright, so there's the path of the ball. As we travel along a horizontal distance, it goes down by a little bit. It goes down by 0.045 every single meter. Okay, when the ball reaches the front of home plate, the height of the ball above the ground is 1.25 meters. 1.25 meters. So the ball reaches the front of home plate. This is the front of home plate. And at this point, the height is equal to 1.25. So this is a geometry question. I always recommend sketching these things up if you're dealing with them. It just helps, I think, gain an understanding, some kind of intuition. The height of the ball changes by a meters as the ball travels over the length of home plate. And here is a meters, this distance right here. Find the value of a. Okay, so we travel a distance of 0.43. And what is the corresponding height difference? So 0.043. We travel a horizontal distance of 0.43. And what we also know is that for every 1 meter, we go down by 0.045. This is our slope. It's our rate of change. In this case, it's negative. So find the value of A. What is the horizontal distance? So for this case, we have negative 0.045. Negative 0.045. This is the rate of change, the slope. And this is what this is saying is we go down by 0.045 meters for every whole meter. But we haven't traveled the whole meter. We've just traveled 0.43 meters. And so in that case, the value of A, this total change in vertical height, is just going to be negative 0.045 times 0.43. Or negative 0.01935 to 3 sig figs, negative 0.0194. All right, justify why this throw is a strike. Why this throw is a strike. So it started off at 1.25 meters. It's going to be a strike if it's between 0.53 and 1.24. So what do we know? 1.25 is where it started. And 1.25 minus A, that is to say, I guess, right before it reaches home plate, we know that it's going down by 0.0194. Oops. I'm going to get some more real estate. I'm going to take this and move it. If I can. There we go. I'll move it here. Okay. And so that means by the time we reach home plate, it's going to be at 0.194. We're going to be at 1.23 meters. And 1.23 meters, it's greater than or equal to, actually no, it has to be greater than, because it's between, greater than 0.53 and less than 1.24. So it's a strike if it's between 0.53 and 1.24. So it is a strike. Alright, there are other ways to work this one out, but I think that one is the most intuitive. Alright. On the next throw, Sakura hits the ball towards a wall that is 5 meters high. Okay, so she hit this ball. The horizontal distance of the wall from the point where the ball was hit is 96 meters. The path of the ball after it is hit can be modeled by the function height as a function of distance. Okay, horizontal distance. And this is the function. In this model, h is the height of the ball above the ground, d is the horizontal distance of the ball from the point where it was hit. Both h and d are measured in meters. Determine whether the ball will go over the wall. Justify your answer. Okay. So this is kind of an interesting question, or at least I think it is. Here is a football pitch, or not a football pitch, a baseball pitch. Looks something like this. And this is, in this case, our radius. This is 96 meters, so in this case this is also 96 meters. This is 96 meters throughout. Okay. And what we're asking, this is also the horizontal distance. The horizontal distance that the ball must travel if it's to go over the wall. From a side view, if there's someone hitting a ball right here, and they want to hit this ball over a 5-meter wall, we have our horizontal distance of h, 96, and the vertical distance d is equal to 5. And we want to find out whether this ball will go over. So I'm going to remove that, bring it over here, so that's fine. Okay. So all this question really is, so far as I see it, is a kind of input-output question. We know the ball needs to be 5 meters high. H needs to be 5, as the distance is equal to 96. So let's find out h is equal to let's find out how high this ball is after it's traveled a distance of 96. This is 96 squared plus 1.04 times 96 plus 0.66. All right, let's go ahead and put that in the calculator. All right, going to the calculator screen. All right, let's go negative. No, let's use this negative right here then. Negative 0.01 and then multiplied by 96 squared, pretty big number, plus 1.04 again times 96 plus 0.66. And there it is. So the height, going back to the document, the height at this point is 7.38 meters. So after this ball has traveled 96 meters, it's 7.38 meters in the air. The wall itself is just 5 meters, so it's cleared the wall. Determine whether the ball will go over the wall. Justify your answer. Why? Because, what can we say? At when D is equal to 96, H equals 7.38. 7.38 is greater than 5. Something like that. Oops. All right. 3 more questions, I think. All right. Vertical posts are to be placed around the outer edge of a children's park. Each post is formed from a cuboid with a right square-based pyramid on top. The cuboid part of the post is machine-made such that its width, and hence the width of the pyramid, exactly 20 centimeters. The length from the apex is the highest point. The apex of the pyramid A to any corner of the base pyramid is 14.6. But, and they've bolded this for us, so it's important, but this is only accurate to the nearest tenth of a centimeter. The post is shown in the diagram. Okay. Write down the upper bound and lower bound for the possible lengths of edge AC. Okay, so they gave us AC is equal to 14.6, but it's only accurate to the nearest tenth of a centimeter, and this is our tenth of a centimeter. And so we can ask ourselves what would be the values that this post could actually be in real life if this is just an estimate. And so what does this mean? If we have, for example, 14.57, of course we're rounding up, but we want to find the absolute lowest value that this could be. In this case, it would be 14.55. 14.55. If it was anything lower, let's say it's 14.54, 999999999, then we would round down. We would round down to 14.5. But if it's 14.55, that's the absolute lowest it can be. Anything lower is actually rounding down. But 14.5 and above, we're rounding to 14.6. And the upper bound in this case will be 14 point, and we can ask ourselves some questions. It was 16, let's say it's 6.4. 6.4 we would certainly round down. But let's imagine the situation where maybe it's 6.45. Then we would still round down. And if it was 6.49, we would still round down. And the question is, what if it's 6.499999, and so on? Then technically we would still round down. And because 14.649999999 going on to infinity is more or less equivalent to 14.65, that would be our upper bound. So if we want to find a possible lower and upper bound for AC, AC is greater than, actually let's write lower bound and upper bound. So let's say lower bound is equal to 14.55, and the upper bound is equal to 14.65. There it is. Determine the upper bound and lower bound for AH. Sorry, the point H is the midpoint of BC. Okay, so we know that this is the midpoint. That's helpful. Determine the upper bound and lower bound for AH. And that's this value right here, AH. Okay. We want to find the upper bound and lower bound for AH, the slant height of the pyramid. Oops, so let's get this back to where it should be. There we go. The slant height of the pyramid. Okay, so let's actually just trace this out. So here's 14.6. It potentially could be a little higher, potentially could be lower. We know that this value right here, since it's a midpoint dividing up this 20, this itself must be 10. 14.6, potentially this could be a little lower. It potentially could be as low as 14.55 or as high as 14.65. So let's determine the max and min for this. Essentially we can use Pythagorean theorem. So let's draw a triangle and see what we can do for the lower bound and upper bound. Let's call this lower bound, and let's call this the upper bound. And let's write two situations. So if we want to find out when this thing is as small as it possibly can be, we know it's 10 for both. And if this is the lower bound and this is the upper bound, this would be, this would be 14.6, 14.55 rather. This would be 14.55, and this would be 14.65. So this is the lowest, this would be the upper, this would be the upper bound, the one on the right. And if we want to find this missing value, let's say this is XL for lower, and this is XU for upper. Oh, let's just say X and Y actually. X and Y. No, X1, X2. Then we can just use our Pythagorean theorem. So what do we know? We know 10 squared plus x1 squared is equal to 14.55. You can n solve this if you want. Sorry, a squared plus b squared equals c squared. That's essentially what we're doing. We're applying our Pythagorean theorem. So I'm going to work this out. 14.55 squared minus 10 squared. Take the square root of all that. The absolute upper bound for x is going to be 10 point. Do they ask us any decimal places? Determine the upper bound and lower bound. Okay, so it's actually just going to be 10.568 or 10.6. Okay. Here we'll do Pythagorean theorem again. 10 squared plus x2 squared is equal to 14.65 squared. Work that out, we can n solve it. 14.465 squared minus 10 squared, and this is going to be x2 is equal to 10.7. Okay. I think we need a little more digits to really reflect that, but I don't see anything asking us for more decimal places. Right. For the post to be safe for children, the angle between the slant height and the base of the pyramid must be less than 22. Okay, so the angle between the slant height and the base must be less than 22. Okay, so what are we talking about here? Let me just erase some of this actually. The angle between the slant height and the base. Okay. So here we are. So we're at the top, and we're going to go right down to the center of this pyramid, and then we'll go off to the side right here. So here we have 90 degree, and this is the angle between the base and the slant height, this theta value right here. To show that it's safe for children, it needs to be less. It needs to be less than 22 degrees. Less than 22 degrees. So when is it going to be less? is it going to be the upper bound or for the lower bound? And I suppose we could just go ahead and try both, but maybe we can save some time and try to work it out. So if we know that this base right here is itself going to be 10, since it's the midpoint, and we know we have either a value of 14.55 or 14.65, if this is fixed at 10, this base is fixed at 10, and we have some value which is equal to either 14.65, or if it's a little longer, and we still have this endpoint right here, imagine this, I mean, this is, let's say, the arm that rotates. If we want to keep it at a same distance, at, let's say, the horizontal distance that it travels has to be fixed at 10, and we want to increase the value of this, then the slant height itself increases as this arm gets longer and longer and longer. So if the slant height, if the angle between the base and the slant height has to be at least, or sorry, has to be less than 22, the angle between the slant height and the base has to be less than 22, let's find out, for the post to be safe for children, the angle between the slant height and the base of the period must be less than 22. So if we take the upper bound, it will be potentially greater than. If it's, take the lower bound, potentially the lower bound could be less than 22, but potentially the upper bound couldn't be. Potentially the upper bound might be more. So let's test the upper bound and see. So let's go ahead and ask that question. Actually, let's do this up here. It's half created. So here's theta. Here's our right angle. The upper bound was 14.65. And let's write out, we have the adjacent and we have the hypotenuse. So remembering sa, ka, toa, adjacent over hypotenuse, we have cos theta is equal to adjacent over hypotenuse. And let's find out. You can end solve this, or we can write this out as cos inverse. So let's go ahead, 10 divided by 14.65, cos inverse. And we have a value of, whoops, sorry, my calculator seems to be in radians. 10 divided by 14.65, cos inverse. There we are. Wow. This is a very large value, which makes me think that something went wrong. Theta is equal to 47 degrees. Okay. Let me look. Just one sec. Let's look at the mark scheme. Go all the way down. This is question 8 or so. Okay, almost there. My apologies. Here we go. No, this is not quite it yet. Okay. It is, okay. So both of these are 46.9 around, 46.9 degrees and so. Okay. It looks like the IB, looks like the mark scheme is actually testing both, but we can think of it, I guess, logically and say that if the upper bound is less than 20 degrees, then the lower bound will certainly be less than 22 as well. But at the same time, maybe it's just best to test out both. Didn't take that long. All right, question 12, and I think there's only one more after that. Okay, let's see. On a specific day, the speed of cars as they pass a speed camera can be modeled by a normal distribution with a mean of 67.3 kilometers an hour. A speed of 75.7 kilometers an hour is 2 standard deviations from the mean. 2 standard deviations from the mean. Find the standard deviation for the speed of the cars. So this is actually really, I think, quite generous question for 2 marks. What do we have? can be modeled by a normal distribution. So they're already telling us we're dealing in the realm of normal distribution. So we're in normal distribution or inverse normal. So not binomial or anything like that. Normal distribution have these kind of bell curves, something like this. And they're centered about the mean. And in this case, the mean is 67.3. And they're telling us a speed of 75.7 is 2 standard deviations of the mean. And we used to call standard, we should not used to, but this is a standard deviation symbol. 2 standard deviations from the mean. What is 1 standard deviation? So 75 minus 7 minus 67.3 divided by 2. This should give us 1 standard deviation. So we know we're 2 standard deviations from the mean. What is 1 standard deviation? 75.7 minus 67.3 divided by 2. This is going to give us 4.2. And that's what 1 standard deviation is. Okay. Speeding tickets are issued to all drivers traveling at a speed greater than 72 kilometers an hour. Find the probability that a randomly selected driver who passes the speed camera receives a speeding ticket. So, speeding tickets to all drivers traveling greater than 72 kilometers an hour. To be honest, I often think these are pretty helpful to visualize. Here's our mean once again. Someone traveling greater than, so if we know this is 67.3, someone's traveling greater than 72 kilometers. Find the probability that a randomly selected receives a speeding ticket. So if they're receiving a speeding ticket, they're in this realm here, this percentage. And we know area under the curve is equal to 1. So let's find out what's the probability someone's in this area right here. To be honest, this would actually be a method mark. Sketching out is an underrated way to get method marks for these kind of questions, I think. Right, find the probability that a randomly selected driver passes the speed ticket receives a speeding ticket, or speeding in this instance. Let's go ahead and let's go back to the calculator. Menu. We want to do statistics, distribution, and in this case we have the value, we want to find the area. Normal is when we have the area and we want to find the value. So the area, actually sorry, it's the other way around. Menu, statistics, stat test, distributions, NormCdf. Lower bound, we can keep it even though someone can't travel negative kilometers in this case. Our upper bound would be 72. Our mean is 67.3. And our standard deviation is 4.2. Alright, so what has gone on here? What does this mean? This 0.868. 0.868. Let's go back to the document and try to unpack this. Speeding tickets are issued to all drivers traveling at a speed of 72. Find the probability that a randomly selected driver passes speed receives a speeding ticket. So what we have is, our calculator gave us this value of 0.868. So what does that mean? That means that all values to the left of this line right here make up 86.8% of the individuals, so 0.868. What does that mean? If it's 100% of the area under the curve, we have 100 minus 86.8 is going to give us the percentage that is remaining over here. Minus 86.8 is equal to 13.2%. And you can work this out as a decimal if you want, 0.868. And 1 minus that. It's actually kind of a challenging question. How about last one in this one? It is found that 82% of the cars on this road travel at speeds between p kilometers an hour and q kilometers an hour, where p is greater than q. This interval includes cars traveling at 74 kilometers an hour. So they want us to show that the region of the normal distribution between P and Q is not symmetrical about the mean. So let's see. So here's a normal distribution. Let's try to see what's going on here. The mean again is 67.3, and they tell us it's not symmetrical. 82% of the drivers on the road travel between P and Q, and it's not symmetrical. It's not symmetrical. And it also includes this value of 74. So let's see. Let's imagine here's P, here's Q. How can we show that it's not symmetrical? Well, to be honest, I think the easiest way might be just to see, okay, well, maybe it is symmetrical. Let's just see, what if it was symmetrical? So if it was symmetrical, we have 82% within this range right here. And so what does that mean? If there's 82% within here, that means that 41% is here and 41% is here. If there's 82, then that means between both this and this, actually let's even use different colors, between this and this must be the remaining 12%, sorry, 18%, which means that 9% must be here and 9% must be here. Right, this must be 9%, this must be 9%. If this is the mean, which divides 50% and 50%, right? Okay, so let's ask the calculator. Let's ask the calculator. The calculator, remember, sweeps out an area from left to right. If we use inverse normal, it sweeps out an area from left to right, and we can use inverse normal to feed it an area, and it'll give us a value in this instance. So let's go ahead and do that. So let's go back to the calculator. So menu, statistics, stat tests. Let's go, distributions. Inverse normal. The area, calculator sweeping out from left to right, is going to be 0.099%. The mean is 67.3, and our standard deviation was 4.2. And let's see what we get. We get 61.6688. So let's go back to the document just for a sec. So let's see. I'm going to erase some of this. Okay. So we imagine that this right here, pink is good. We imagine that this lower bound is 61.6688 or 61.7. And if it's symmetrical, then that means this distance right here, this distance between P and 67.3 must equal this distance between the mean and Q. So 67.3 minus 61.7 is equal to 5.6. And if it is again symmetrical, that you get a mirror reflection, then this as well has to be 5.6. And 67.3 plus 5.6 gives us a value of Q of 72.9. And we can ask ourselves, no, that can't be, because this itself must be equal to, it includes cars traveling at a speed of 74. And so what can we say? We can say that 72.9 is less than 74. And this, to be honest, this would be, a very nice method as well. I think it's easy to understand what's going on. I don't know if you need this top part so much, but what's on the bottom, yeah, would be great. Show that the region of the normal distribution between P and Q is not symmetrical about the mean. Well, we tested whether it would be symmetrical, and we found out no, it can't be. 82% travel between here. It can't include the 74, because if it would need to be its upper bound is at 72.9. All right, last one. Made it. Just about there. 5-mark question, final question. Often they're quite challenging. I imagine this one is no different. Okay. It's bearings. Bearings are something that aren't often very thoroughly covered. This was the first bearings question that I had seen on these May exams. Actually the next November's exam also had a bearings question, which is kind of funny. It's possibly because students performed poorly, maybe on the previous one. I'm not sure if that's the logic, but it happened to show up twice in a row, which is kind of funny. All right, let's see what we can do. A boat travels 8 kilometers on a bearing of 315 degrees, and then a further 6 kilometers on a bearing of 45 degrees. Find the bearing on which the boat should travel. It should return directly to the starting point. 5-mark question, just one big question. Okay. So what are we talking about? When we're talking about bearings, we are talking about our directional coordinates. Never eat north, east, southwest, and so on. So let's try to look at what's going on here and see what we can do. A boat travels 8 kilometers on a bearing of 315 degrees. So bearings are always measured in relation to true north. So if this is true north right here, we want to sweep through an angle of 315 degrees and then set off on our way. I'm going to move this down just because it looks like it will be helpful if I do. Okay, so here's true north, and we want to sweep through an angle of 315 degrees. So if this is 90 right here, this is 180, this is 270, and we're going to sweep through an angle that is 315 degrees. 315 degrees, something like this. We should be okay. And we've traveled a distance of 8 kilometers. To be honest, I think this should actually be bigger. Just because often bearing questions are going to contain a lot of information in a tiny space. It makes it a little challenging. So let's go ahead and write this out as 8 kilometers. And again, we sweep through an angle of 315 degrees. All right. After that, we travel on a bearing of 45 degrees for 6 kilometers. So once again, let's draw true north. Here it is, true north. And we travel off on a bearing of 45 degrees. So we sweep through an angle of 45 degrees. And we do something like this. And we do that for, what can we say? Actually, I'm going to change this just slightly. 45 degrees, something like that. 45 degrees? Yeah, I'd say so. 45 degrees for 6 kilometers. And so once again, this is 45 degrees. And the question is, find the bearing which the boat should travel to return directly to the starting point. So here's true north once again. And the question is, what angle do we need to sweep through to go back home? This is what we're trying to find, this theta value. Okay. Let's see what we can do. Okay. So generally these questions relate to the interior angles of this triangle that emerges, and then we would need to use a combination of sine and cosine to try to work things out. And then also using our angle laws. So if we have, for example, 2 parallel lines and then some line cut between here. So first thing that we could potentially use is this value right here. I'm going to switch to red. If we know we've swept through 315 degrees right here, we know that this right here must be equal to the remainder. So angles at a point, one full rotation is 316. We know that this is 45 degrees. 45 plus 315 makes a whole. And if we know, for example, like this is A and this is B, we know that A plus B, these two co-interior angles, equal 180 degrees. Just a kind of insight into that. If this is B and this is a, they make 180, and this are both the same. So a plus b is equal to 180. Okay, 45 degrees, and we know that then this right here has to complete this. So this 45 degrees plus 45 degrees plus what gives us 180. If they have to sum, this would be 135 degrees. So we know that this is 135 degrees. And this is interesting, this is helpful, and this is very nice. 45 degrees right here, this is 135 degrees. If we take away 45 from 135, 135 is us sweeping through this whole thing. But if we're just sweeping up to the point, so I know I'm using a lot of colors here, if we're just sweeping up to this point, that's not a good color, we're just sweeping up to this point right here, we've swept some value, 135 less 45 is how much we've swept. We haven't swept the whole 135, we've swept almost 135, but 45 less than that. So 135 degrees minus 45 degrees gives us, and this should be a deep kind of moment of exhalation, 90 degrees, because thank goodness we've got a 90-degree triangle, and that should make things a lot easier. So let's go ahead and simplify things and just write 90 degrees. Excellent. 90-degree triangle. We know that we don't yet actually have any interior angles of this triangle yet. So we're going to have to find some. But we know this is 90 degrees. If we have a 90-degree triangle, we should be able to find all the other angles of the triangle. So let's find this angle right here. So let's call this theta. If this is theta 1 that we want to find, actually no, let's call this something else. I'm going to call it beta. That'll do. Okay. So we want to find beta. Let's see what we can do. We have the opposite and we have an adjacent. So let's use tan. Tan beta is equal to opposite over adjacent. We're actually almost to the answer. You can end solve this, or you can use tan inverse. Let's see, tan inverse 8 over 6 is equal to beta is equal to 53.1 degrees. 53.1 degrees. Okay. Good. 53.1 degrees. And let's actually go ahead and write that. Let's replace this with 53.1 degrees. So why this angle? Why this one of all? Because if we continue with our angle pairs, we know that this right here, this side length, or sorry, this angle is 45 degrees. And we know if this is 45 degrees, then we know that this has to be 135 degrees, because we're drawing again on this angle relationship here. Co-interior angles sum to 180 degrees. So if we know this is 135, we know this here is 53, we have this relationship in the end. 135 degrees plus 53.1 degrees plus theta, what we're trying to solve, has to equal to 360 altogether. You can unsolve this or just take away from 360 degrees. 360 minus 53.1 minus 135 tells us that we need to set off on a bearing of 171.9, or to 3 sig figs, 172 degrees. All right, and there it is. Quite a challenging question. A lot going on there, but generally this one is actually kind of nice because a right angle triangle emerged, but often we need to use our our angle relationships. So in this case, our co-interior angles are often super helpful. Here's our co-interior angles. Here would be another set of co-interior angles. This, for example, right here, and this is a co-interior angle. So true north, two parallel lines cut by some line. Alright, that is this exam. I hope it's helpful, and best of luck. Bye-bye.